Okay, so first, back to the mining complex. So the goal here was basically to evaluate the potential of the stochastic mining planning. We had some assessments of the deterministic, but we wanted to know if we could unlock more value on the project. So the mineral deposit here is a common iron ore formation where we have a few lithologies that we are mostly interested in. In which we highlight here we had like Kanga, hematites, itabirites, manganese-rich itabirites as well that would play an important factor on the project, and other waste material that were composed mostly by quartzites. So related to the complex in the facilities overall, we are dealing with a one deposit. We had a possibility to stockpile material. We had one waste dump and two different processors that would generate different products. So the first product was a direct shipping ore, which only is concerned with the granulometry of the product. So we assumed 100% mass recovery, and because of this, we needed to take care of the quality of the material arriving, because there wouldn't be any concentration step in this part. And because of this, the only lithology qualified to feed the processor was hematite ore. And for the pellet feed plant, so this involved milling and flotation. So there was a certain recovery, mass recovery associated with that was dependent on the different deleterious elements. This was a nonlinear, very nonlinear recovery curve that was which was function of several deleterious elements and also the iron content. And there were two types of products that this facility could produce. One was a direct reduction pellet feed and a blast furnace pellet feed, with a slightly different prices. The direct reduction ore would have a premium associated with. So the mining complex would have to balance material going to the DSEO plant, which would incur a smaller processing cost, but also a smaller financial return. Whereas at the pellet feed plant, we have more valuable material coming out, but at the cost of a higher processing cost and smaller recovery. And because of this nonlinear function, we needed to take care of the amount of hematite that could feed the process, because we've just used the equation as it was. Due to the high grades of iron and low on silica of the hematite, the mass recovery would be very high given the equation we had. But what we see in reality is with the circuit passing a very rich material as input, we wouldn't generate as much recovery, and we would end up having tailings with a high content of iron. So we limit a certain amount of hematite that could feed this processor. And we also allow the manganese-rich itabirites to also feed this process, as long as we take a very good control of the manganese target at this processor, which was one point of a concern of the project. So just some details of the ore biomodeling. As I mentioned before, we have some mineralized units here. We had hematite rocks, which were subdivided into low and high phosphorus. And the itabirites were subcategorized into manganese-rich and poor and rich manganese content. And for waste, we have several types of materials that were aggregated into a single unit, which mostly were characterized by the quartzites. And regarding the simulations, so for this specific case study, we didn't have much time to simulate the lithologies, but this is something we're going to do for future works. But we simulated correlated elements related to iron, silica, manganese, phosphorus, loss of ignition, and so on. So the first thing we were interested in was the doing some analysis on the possible contaminants. And the first one that we were interested in was phosphorus, because this could impact the quality of the iron concentrate, decreasing the quality of the steel that would be generated afterwards. And there's usually it's common to have a deduction on the price if the product doesn't meet a certain target on phosphorus. So the deterministic model, we already know we're seeing some limitations of the deterministic approach that would smooth the variability of the data. So on top of this, with the approach using the intrinsic model of corrosionalization, there was not much flexibility to model all the deleterious elements, which end up having which was another point of concern. So we used the simulations to address that. So just some visual, some examples of the attributes we simulated. So first here we see the variability on the iron grades. And most of the time we have iron grades, they do not vary drastically from one simulation to another. But what we saw was an important difference between the simulations and the deterministic model, especially for the hematites. And we will see in the results some impact of this distance by looking at the grid tonnage curves here. We end up also simulating manganese. So, and for this deposit, the bottom part was a bit richer in this material. So that's why you have more variability and also higher grades at the bottom part. And this is something, this material was this attribute was one of important aspect that we wanted to take care at the processing plant, because given this smoothing effect present in the estimated model, what we end up seeing in the deposit is a much higher grades of manganese that could impact the product. So we need to take this in advance. And also, depending on the cutoff that we end up using, there is more or less material available. And same story for phosphorus, but the only difference that there is a greater variability and presence of phosphorus in the top part of the deposit, which would affect the early years of the operation. So same story here in terms of the smoothing effect that we see constantly. So then let's take a look at what happens with the schedule. So for this part, we didn't have access to the whole schedule, which blocks go where. So we end up taking the shells of the different periods and take a look at the content of phosphorus in this for each year. Not exactly going to the processor or to the waste dump, but the overall material at that period. And we have here in the red line the estimated value, and everything within the dashed lines represent the difference between the P5 and the P95 percentiles. So as you can see, there is a very high variability in the first year, as we saw that this was more present in the top parts of the deposit, and also in the year two we have a large range of variability. So what we did here was to investigate what was the probability of underestimate the amount of phosphorus, since this could impact the generation of product. And especially at this first part, there was a very large chance of underestimating the amount of phosphorus. So for the second year, in terms of probability, this number was not so big, but there is a very large range in which that could impact the products. So same thing for the rest of the life of mine, with large chances of deviating by a lot, and even in the final years there is even 100% chance of that the deterministic model underestimated the content of this element. So then we ask ourselves to be if we could do better, if we could use this information and unlock the potential to generate more or increase value of the project. So then we studied a few cases. So we had access to the production plan of the deterministic, but we don't have the full schedule. So we're just going to be comparing against the numbers reported by the deterministic. We didn't run a risk analysis on it. And moving forward, we had 3 different stochastic optimizations. So for the first one in green, we optimized the whole value chain, and but only used what was initially characterized as a measure and indicated O to feed the processor. The next step, we wanted to see if there was an additional potential of what would bring if we consider the inferred material as well. And finally, we wanted to see if the forecast that we have for future iron ore prices could bring even more material into the game. So for the first comparison here, I'm going to be comparing the stochastic optimization versus the base case. So the base case is presented in black, and for the stochastic optimization in green. And the schedule of the stochastic is here on the left-hand side. And what we end up seeing is that the stochastic optimization was able to increase in up to 2 years the life of the mine. So meaning more run of mine being sent to the processors. And there was also an important aspect that we saw was we were able to feed the processing plant with a more constant throughput for especially earlier up in this 10 to 13th year. In terms of the products that we generate, both the pellet feed and the DSO. So for the DSO, we had an increase of 16% overall, considering the whole life of mine. With the regarding the combination of both direct reduction and blast furnace pellet feed fines, we have the deterministic model was a little bit bigger, so the stochastic forecasted up to 3.5% less product. So even though, so in this case, even though we end up providing more or similar run of mine, given the mass recovery that was different for the different optimizations, we end up having less. But in overall, summing both type of products, we end up having 60% more products. So as I was mentioning, one of the reasons of producing less was that the deterministic was forecasting a higher recovery of the material most of the time. And if we had the access to the whole schedule, we could run a risk analysis and see if this is, would follow close. But my guess would be probably a bit lower than was actually expected. Since that most of, as we saw with the grade tonnage curve, that we were underestimating the grades of iron, silicon, and others. And another point of concern was if we're be able to reach to respect the targets in terms of manganese here. And what we saw was that the stochastic optimization was able to respect very well for most of the time, and even to push riskier periods to later, and even though by a not great margin. The P50 was always within the target. So the second comparison that we studied was now having the stochastic optimization considering inputting the inferred material as well, and compared to the stochastic optimization. And what we saw is an additional gain of 2 years in terms of a life of mine. So both the DSO plant and the pellet feed plant profited from receiving more material for longer periods. And in terms of products, we generate 4% more DSO and up to 9% more pellet feed. And also here in the left-hand side, in the bottom, we see schedule the physical sequence of extraction related to this optimization, which differs from the previous. So similar things here. We have similar results in terms of the head grades of iron feeding the processing plant, with just the one difference in the first year. By allowing inferred material, we end up decreasing a little bit iron grades for the first year, but most of the time seems pretty consistent. Mass recovery also seems consistent and stable throughout the life of mine. And again, we were able to respect the targets related to manganese. So the last comparison, we wanted to see if we could bring even more value by considering optimistic prices, if this would encourage bring more ore in deeper areas. And compare it to the stochastic optimization, considering only measured and indicated material, we see again 2 years of increase of 2 years in life of mine. The schedule that we generate is again different, and we have up to 8.4% increase in the amount of products that we generate. Same story here in terms of head grades, mass recovery, and respecting the different targets, important targets we have. And in terms of just to summarize the comparisons here and try to bring something more comparable given our cases. So the first set of first graph here is a comparison in terms of the run of mine. So this was what was reported by the base case, the deterministic case. And by running a stochastic optimization, we end up having 4% more ROM feeding both process, so DSO, and the pellet feed. By allowing inferred material, we had an increase of 7%. And we didn't have much increase just by including inferred and having optimistic prices. In terms of sorry about the label here. So this is the amount of products. So this was what was reported by the base case. So in total, we have almost a 6% increase using the first stochastic optimization, and an additional 6.5% on top of this by including inferred material, and only 0.6% on top of this using optimistic prices. So what we saw here is that including inferred material, we had a important increase in terms of products, extending the life of mine, but that didn't end up improving much the NPV. Just note that for this case, we didn't have the NPV of the base case, so we are comparing against the initial stochastic optimization. So using the inferred didn't increase much the NPV compared to the stochastic optimization, but having the optimistic prices, there was a substantial increase in terms of NPV, even though we didn't have this didn't generate much products afterwards. So now moving to the conclusions. So here we generated simulations to help us understand the role of especially the deleterious elements in the deposits, which was more critical to this project. And we saw that the stochastic optimization was able to unlock value by extending the life of mine by 2 or 4 years, depending on the materials that we are feeding the processor. And we're able to run the pellet feed plant for longer, at the full capacity for longer, and which generated the potential to produce more concentrate. What was initially a potential concern related to the manganese, we were able to maintain it at acceptable limits and postpone risk to further periods. Specifically to the case where we allowed inferred ore into the optimization, this led to a small increment in NPV, but an interesting one in terms of amount of products that we can generate and run the mine for longer. And related to the optimistic prices, we didn't change much the production forecast, but that impacted the schedule, the physical schedule, and substantially improved NPV. So for future work, we'd like to assess uncertainty also in terms of lithologies on top of the current framework that we've been simulating correlated elements, and keep this as a common practice for the different products we end up evaluating. And also include other pits in the vicinity so we could profit from the existing synergies in a larger mining complex. So that's what I have for today. Now I would welcome questions if you have any.